Well, welcome everyone. This is the eighth such follow-up event, and we are going to be looking through the March issue of the British Sundial Society Bulletin. I will now share my screen. Well, this is the going to be looking at the March 2025 issue of the Bulletin, and as always, I give you my email address so that you can comment, grumble, or whatever. And if you want to look at previous versions of these follow-ups, you just search the British Sundial Society YouTube and you will be able to quickly get to the place where the previous versions are held. If you want to go there directly, you key in youtube.com @ the-BSS. Here is the abbreviated list of contents for this issue, and it's a bit thinner than usual, but we discovered at rehearsal that doesn't mean there isn't anything to discuss. We actually had quite a long rehearsal. Various things cropped up. The lead article is by John Davis, whom I'm delighted to see is with us. So in a moment, I'll be handing over to him for giving us a bit of background information. I'm also going to highlight the ceiling heliochromometer article by Andrew Hodson, who is going to be looking after the postscript at the end. So I think if Martins, if you could show us the bulletin, that's the front cover, and we go inside. And there you can see the contents again, a bit smaller, the editorial, but on the next page we have the start of the lead article by John Davis. And John, if you are really there, I think you are, perhaps you can give us some comments.
Volumes are rather low at my end, but I'll talk loudly and hopefully you can hear.
But we can hear very well.
Right. Okay, shall I start?
Yes?
Right, okay, well, I was first informed about this dial by Steve Butchko in the States, and he sent me some pictures and he wanted to buy a copy of the monograph on double horizontals, which I'm glad to say we could provide. And it's a very nice dial, which was unrecorded, it's unsigned, and that really was the sort of the heart of the investigations. Who made it? It's pretty obviously by looking at it that it's a very early one. It's got the months of the year rather than the signs of the zodiac across the ecliptic arc, and that means it's almost certainly come out of Elias Allen's workshop in the 1630s. And Stephen said he thought it was by Elias Allen himself. And I was a little bit sceptical about that because I've had claims like that made before and we've proved it to be wrong. But so we kept looking and we found plenty of evidence to suggest that he did actually right. Elias Allen has made this rather large double horizontal, large for him anyway, and either forgotten or decided not to sign it. Quite how it got to America is another mystery, which I don't suppose we'll ever solve. But you can see Martins has put up the picture of the overall dial. The gnomon is broken just where it thins down to the tail, and that's about 60% of the dials that are like that. It's quite a thin metal, and it's a casting, so it's pretty weak. So they all break. But luckily, as you can see from the shadow, the two bits of the shadow that really matter are still effective. I don't think it's set up to show a particular time there, but you can see that it certainly would tell the time. If we move on to the next picture, to some of the details of the dial, can we move on?
This one? Figure number 2.
Can we have the figure 2?
I'm trying to show it.
This is figure 2. We can see figure 2.
Yes, it's figure 2. Or
yeah, okay. Now, what you should see there, and Frank's eyesight wasn't up to it, but we managed to find it in the end. There's a row of dots which go from the tip of the gnomon running due south, so that's sort of halfway between the V111 and the 11 whatever it is on the other side. And those row of dots you see on almost all double horizontals, and they're the centres of the declination arcs. So there's quite a lot of them. They start underneath the gnomon and they run right off the edge of the gnomon at the dial disc at the south. But they're very, very characteristic of a well-made double horizontal. If they're going to make a coat of arms in that area, then sometimes they would take those marks out after they've struck the arcs. But obviously they didn't bother here. So if we move on to the next figure, figure 3. Can we have figure 3?
Yes, here it is.
Yes, we've
Possibly
got.
there's some delay in showing the image at your side.
It's coming through clear to me. I think John
I
has a
got a
web
message
screen.
just now saying my internet connection. There we go. Right, that's figure 3. Now this one caused some problems because you can see just above halfway. Martins is actually highlighting it there. There's a row of dots very close together, running from sort of halfway down the gnomon. Now, no one knows what they're there for. They've not been seen on any other dial. So a few years, how you might use those. I and Stephen would be very, very grateful to hear them and to try and work out what's going on there. But anyway, they don't sort of prove things one way or another in terms of who made it.
I could add that
So
neither Andrew nor
anyway,
I
looking
had
at the
any
dial overall,
explanation.
yeah, happy, Frank?
Yes, I was just wondering
Can I
whether
go on?
anybody. I was wondering whether anybody listening in could give any ideas about these dots. So if you have a thought about these dots, do raise a hand, and you can keep your hand raised at any time during this whole session. But at rehearsal, none of us did think of a good solution as to what these dots are all about.
Okay, so what we've established so far then is that this dial was almost certainly made in Elias Allen's workshop, but he had a lot of apprentices working for him, and so it's conceivable that one of them made it. And obviously apprentices weren't allowed to sign dials, but the head of the workshop, the master, would sign on their behalf. But if we go on to the next figures.
Figure number 4.
Yeah.
It's a backside.
Right. Okay. Okay. Well, they're two fairly standard pictures, so perhaps we can go. And that's the back of the dial, which is not particularly interesting, other than the fact that it's been hammered around the outside to thin the metal down, probably. Perhaps it was over thickness to start with, or perhaps it wasn't quite the right diameter, and they wanted to stretch it out. But it's just an interesting sideline of these very, very, very handmade dials.
Okay,
Can we
right
keep
now
going? Over the
go
page,
to
please.
figure number 5 or next page.
Next page.
Okay.
Next page, yeah.
Okay. Sorry. Yep. It's here.
Five really just shows you, if you've never seen a stereographic projection close up, this is what you actually see. But you can't get any more information from that. But figures 5 and 6 are critical.
Yep. We have it.
Yes, we can see it. We can see
There we go,
September.
6 and
April.
7. Okay, so Elias Allen has got a very peculiar engraving style in a couple of different ways. And first of all, his letter P's, lowercase p's, he writes them in a strange way where he doesn't close the top of the P, and it looks more like a Y with the descender on the left. And as far as I can see, no one else does that, not even his apprentices. So that's, as far as I'm concerned, that's a very strong pointer that Elias Allen engraved this with his own hands. And the other thing that's different is in the next figure, figure 7, and what you see there is rather sharp edge to the figure 2. It's not very fluent, and that's really because he was an early engraver and he was sort of learning as he went, I think. So that again, the number 2 looking rather like a Z is very much an Elias Allen trait. So with that, I came to the end of the conclusion was that I was pretty certain that it was an Elias Allen dial, handmade by him. But there's one other factor of double horizontals which I mentioned in the last paragraph, and that's the metal that he used. He had a source of supply of not even his apprentices got access to this. It made the dials look rather nice and golden in colour when they were polished up and new. So he obviously kept them to himself. It came from the Netherlands, I think, from around the Leuven area. And what I said in the article was that we were hoping to get that tested. What I didn't realise was that Steve Butko was really very active, and within weeks of doing that, he did test it. But unfortunately, the article had already gone to press, so we were unable to publish the results, but they will be in the June Bulletin. So look out in the June Bulletin for an addendum where we find exactly what I was predicting. The dial plate has got a very high level of zinc, over 30%, and that's almost certainly really sort of crosses the T's and dots the I's that this is a handmade dial by Elias Allen personally, and why he didn't sign it is left for the future. Frank brought up earlier a fact of a mistake I made. The dial has got a scale for the altitude. You can pick off the altitude of the sun at any given time, and I said the scale was only delineated up to 66 degrees, because that's the height that the sun can reach in London. And Frank pulled me up on my mental arithmetic, quite rightly, because in London the sun only gets to 62 degrees. In fact, when you look at the scale, it's very difficult to tell how far the scale goes, because the best pictures we've got are a little bit out of focus. But anyway, they didn't bother engraving all the way up to 90 degrees, which would have been right at the base of the gnomon, because the sun was never going to get that high. I think I had 66 in my head, because that's the Arctic Circle. If you take the obliquity as 24 degrees. But anyway, that was my mistake, and I'm sorry about that. So that's it, really. Another double horizontal dial. Number 89 now in the catalogue, and I might say we're up to 91 since that one was done. So it's going to be a big celebration when we get to 100 double horizontal dials, hopefully in my lifetime. Thank you very much. Any questions?
Thank you. Yes. Anybody got any hands raised, Martins? Can you see?
Not currently, but you can raise hands or just start speaking as well.
Can you hear me?
Yes.
I would like to make a comment to those strange dotted lines. I'm quite certain that they have been done afterwards, possibly by the owner, and has some reference to the location where the sundial was placed. Because if you compare the quality of the work to the engraving on the dial, I mean, this is not even a straight line, and somebody was probably not even able to cut lines in there. I think it has been done afterwards.
So
And might have some reference to the location, perhaps. Would be good to look that up, because it's in quality much lower than what you are on the other compared to the other engraving on the dial.
well, that's an interesting point, Thomas. If you were going to say it's pointing to noon at some location, then what I would say is that it's coming from the wrong point. You can see that the line is nowhere near parallel any of the hour lines. So you do get longitudinal markings on dials, but they would come from the centre of delineation, which is at the tip of the gnomon.
Yeah.
So I'm not sure how it would work in this case. Have you got an
But
idea about that?
but the quality of the engraving, it's not even an engraving. It's much lower than the rest of the dial.
Yes. So
No, I'm not sure I agree with that.
somebody playing later date.
It's
Anyone else got,
possible.
anyone else got a hypothesis? Otherwise, I think we say thank you very much, John, and you can move on to Andrew, to the next page, where we have this dial on the Isles of Scilly. The Isles of Scilly are off the southwest coast of mainland Britain, mainland England in this case. And this is a very small island, and it's quite a complicated place to get to. You have to go to one of the bigger islands and then take a boat across to this island. So the logistics of setting up this sundial are quite challenging, but otherwise it's quite an ordinary sundial in a very unusual place. If anybody's got any comments, by all means, tell us. Otherwise, we will move on to the next page. And this describes a sundial in Brazil. This is unusual for us. We don't often get sundials which are very obviously in the southern hemisphere, but this one is a case in point. It's a rather strange sundial in that, I'm talking about the sundial at the bottom left-hand corner of that page, rather than the top one. It has some hour lines, and it has these two analemmas. And do notice that this is an analemma on a horizontal surface. And if you try to produce an analemma on a horizontal surface in England or anywhere in the Northern Hemisphere, around 40, 50 degrees north, you would find that on a horizontal surface, the little loop will be very, very much thinner than that loop, and will be utterly dominated by the large loop. Whereas in the southern hemisphere, because things are, as it were, the wrong way round, the smaller loop is actually maybe 1/3 across of the larger loop, and looks actually more interesting on the southern hemisphere than it would on a horizontal sundial in our latitude. I don't have anything more to say about that article, but maybe other people would like to comment on the strange instrument on the right-hand page, or indeed about the sundial at Brasenose College, Oxford, which is the next mini article on the right, the potpourri postcard. I see no raised hands, so let's.
I have a little question,
Yes.
which is, it mentions the fact that when you're in these sunny countries, you don't get many sundials. And I'm wondering if there was a received wisdom as to why that is. Why in rainy Britain do we love sundials? And why in France or Italy you hardly see one from one day to the next?
Oh, well, you'll see many, many, many sundials in Italy. There are literally thousands of them. And the sundial atlas is dominated by Italian sundials. But I do agree with you about the southern hemisphere. There aren't that many. And maybe by the time the imperialists of the of Europe were opening up the southern hemisphere, sundials were going out and clocks were starting to come in, so they didn't get a chance to catch on in the same way. But it is a good point. We really don't see very many in the southern hemisphere. Perhaps once every couple of years in the bulletin. It is nice. These are all the ones that, certainly on the left-hand page there, are much the same place. And you can see these sundials on Google Maps, Google Street View. So it tells you the latitude and longitude. Go and have a look, and you can see where they are. They're quite big, so they can be seen in what they call satellite view. Any others? If not, let's go on to the next page is the annual report of the trustees. That's not something of any interest to those people who are signed in here, but it does give me as chairman an opportunity to say thank you very much to all our volunteers, many of whom have given little snippets of contribution to this trustees report, and I thank them very much for all their hard work during the past year. Well, now we look on to the newly reported sundials, and there are a good many of them. And it just occurred to me that somebody signed in will know some of these sundials, in which case you can perhaps tell us a bit more about them. And somewhat surprisingly, sundial number 2 prompted quite a lot of discussion at the rehearsal. As it happens, that this sundial that Martins is showing now is about a 5-minute walk from where I'm sitting at this very moment, and the photograph was taken by Christine Northeast, who lives probably about a 2-minute walk from it, and the third person at rehearsal on Monday was Andrew Hodson, who lives perhaps a 15-minute walk. So it's not far from some people signed in. If you look carefully at this view, you'll see that we obviously have an armillary sphere sitting in a hemispherical cradle, and it is absolutely at the wrong angle. You can, if Andrew Martins, can you draw attention to the gnomon? The gnomon is absolutely horizontal, which would be appropriate for the equator, but is absolutely hopeless for Cambridge, which is just over 52 degrees north. But it's all the right parts. Just if you lifted that up and turned it around and moved it about a bit, you could have it as a very satisfactory working sundial. It's got the hour numbers on the equatorial ring, which is more or less in a vertical plane here. And it's got a motto around the side in Italian, and Andrew found out where that was from. But it's in a very silly place, as you can see. When you view it in this way, it's entangling with the television antennae. Perhaps go back to the page in the bulletin.
Yes.
And if we just go through the next pages or two, there is that page we have there at the top, one of my favorites, of course, another double horizontal sundial, which David Brown claims is the only slate double horizontal sundial in a known location. I'm not altogether sure that's true. Is it? It doesn't. Joanna Migdal's slate horizontal sundial have a known location. Some college in Oxford, whose name I've momentarily forgotten. Somebody can perhaps remind me. St Hilda's. It was one of the women's colleges, what used to be one of the women's colleges. I think they're all mixed now. But this one by David Brown is jolly nice. And as you can see, he's got an altitude scale, which is the sort that you can rotate about the very bottom of the vertical element of the gnomon, the knife edge, which is quite unlike the arrangement in the Elias Allendale we saw earlier. Do raise a hand if you've got anything to say about any of these sundials. There's some fairly straightforward sundials on the right-hand page. In particular, bottom right, you can see one by our patron, Mark Lennox Boyd. That's in somebody's lawn, the client's lawn, and I do think literally in the lawn. This is very vulnerable to a stray lawnmower, so I wonder how long that's going to last. And over to the next page where there are some more of note.
We had some discussion about sundial number 15.
Yes, can you go close in on number 15? This is very strange sundial, and several people have had attempts to explain some logic to the way the numbers are arranged. Because the numbers, at the first glance at least, the numbers at the bottom, the 5 in a row from 10, 11, 12, 1 and 2 are perfectly conventional. The numbers are arranged so as to be read from somebody standing at ground level looking up, all perfectly normal. But if you look at the left-hand edge, the numbers are designed to be read by somebody crawling along the inside of the main chapter ring, perhaps right at the center of the dial, just below the A of aura. And you can see that the 6 is written IV if you read it in the ordinary sort of way. And there are dials in Cornwall which are referred to by John Fode, who wrote the associated article, where the shadow goes round, obviously in an anti-clockwise way. And if you think of a shadow going around anti-clockwise, it meets the V before the I. And so you think, oh yes, V plus I, or 5 plus 1 makes 6. And likewise, 5 plus 1 makes 7, and so on. But the V's are the wrong way around. The strong serif is in heraldic terms a ben sinister rather than a ben dexter, and this is not the way around that you would see the letter V cut in stone in ancient Rome. So something very odd going on here, as several people will have had several conjectures, but I think Sue Manston, I don't know, is Sue still with us? Had the best comment, which is that there is no logic to this, it's just peculiar. And I think that's the only sensible thing to say. Maybe somebody listening, watching can tell us more about this, because it's not unusual. There are other dials like this, though not, I think, with the V's the wrong way around as here. Just by coincidence, this actual sundial is a couple of miles from where I lived in my childhood, but I had no idea about sundials in those days. Otherwise, I would have gone and investigated this one. Right, so if you can pull out again, Martins, and have a look at the others. Nothing that I saw of immediate note. The one, yes, this is the final few pages. Quite an interesting one at the top there. But then we come on to the, this is Andrew's article on the ceiling heliochronometer sundial, which he's going to be talking about in the postscript. So by tradition, we won't discuss it now, but we're almost at the end anyway. So I think carry on to the next page. Next article, where we see the bulletin follow-up, complete with a discussion about the rings on a sundial. Yes, a picture of my ball with some elastic bands on it. I strongly recommend this. If you just have a close look, Martin, if you can have a look at the picture of a globe. These globe dials cost about £1. Well, I bought that one for very cheaply from the far sale at Wilko's, and it just by chance is the right diameter for the elastic bands which you keep finding in the streets. And if you don't understand the mathematics of spherical triangles, well, this is an answer for you, because any spherical triangle can be depicted with 3 elastic bands, and immediately you discover that there are 7 other spherical triangles, and you can actually make measurements approximately by measuring the lengths and the angles between them. And so this is, as it were, a poor man's way of understanding spherical triangles. I won't dwell upon that, but it's just something to note. And the very last thing is a book review. It is possible that either Kevin and or Martin Jenkins, who wrote the book review, are with us. This is a newish book by a noted member of the British Sundial Society, Kevin Carney, where he tells you absolutely everything you ever wanted to know, and perhaps a bit more, about the equation of time. Well, I think now, unless anybody's got any questions, no raised hands that I can see. if we can hand over to you, Andrew, and so Martins will unshare the screen, and Andrew, you can share your screen or do whatever it is that you fancy at this stage.
Perfect. Thank you, Frank. So yes, this is a bit more background and a few more photos and a bit of a live demo of this monstrosity that I constructed over several years in my house in Surrey. No longer in the house in Surrey, I'm now in Cambridge. So I had to dig it out of the cupboard where it was gathering dust. But I will, if I can move this about, you can see here the user interface generated by the Raspberry Pi. And if we look behind the TV, we can see the thing itself. Just make sure that you can see it.
Andrew, can you pause a moment and recommend people go into speaker view rather than gallery view if they want to see this enlarged?
Yes, good idea.
So if you're watching, please go into speaker view rather than gallery view, and then you can see his instrument with the pan and tilt.
Is that visible? Yeah, okay. So basically a Raspberry Pi is a very small computer that I'm sure you guys, many of you will be familiar with. This is the Raspberry Pi itself. It's a very tiny thing. It just needs 5 volts to make it go. It has a USB output, which I'm splitting here. And from that USB output, I'm driving 2 servos, which are essentially stepper motors with a feedback board. I will talk about a little bit more. And then on the end of this limb here, on the end of this axle, I've got a laser, which is probably shining directly into the camera and therefore not coming out very well. If I, at the moment, because the sun is, if you were in Surrey with my south-facing room, you would find that the sun basically was no longer reflecting onto the ceiling. So the laser is currently at pointing at the ceiling rose, which is where I park it when it's off the ceiling. But if I, for instance, type in that I want to pretend that it's noon today, you'll see, hopefully you'll see it move. There we go. And I can make it go at different speeds. I can make it go to 9 o'clock in the morning today, and it will zoom back around to there. So you can see it moves reasonably quietly and reasonably quickly. And in the normal mode, it just sits there and runs in real time. So in an ideal world, the laser spot on the ceiling, which I won't show you because it doesn't really show up and it will just make everyone a bit seasick if I try and angle it in. The spot should in principle follow the reflection of the sun on the ceiling, which is reflected from a little mirror on a bracket outside on the window frame. I don't have one here because my current front room, sitting room, doesn't face south, unfortunately. So if we look at the user interface, tell me if that is at all legible. You can see that's on my 55-inch TV. And unfortunately, I can't see it because although I'm in speaker view, I don't show it for myself, which is a bit irritating. There we go. So you can see here that every 8 seconds, it redoes the calculation. So you can see it 1634, 1636 and 32 seconds. It's running at 1's time real time, and I can make it run faster and double the speed and quadruple and 8-fold the speed. And currently, last thing I did was to set it to 9 AM. So you can see it's now showing 9:01. And then we get the sun's azimuth and elevation calculated. Then we calculate where is the spot on the ceiling using the coordinate system, whereby the x-axis is east-west, the y-axis is north-south, and the z-axis is vertical. So there's a basic assumption in here that the whole of the ceiling is at Z equals 0. And we'll come back to that as quite a flaw in this whole project. Then it calculates what the laser azimuth and elevation should be. And you can see it's a nice healthy elevation at 9 in the morning. The elevation is at 61 degrees. If I change that back to where we are now, by typing now in there, it will parse that and come back to the real time now, which is 1637. So you can now see that the elevation of the laser is now 14 degrees, which is too low and is in danger of blinding my family. So instead of pointing it at, I pointed at the ceiling rose, which is where it's parked when the sun isn't, when the dot, sunlight, the reflected dot isn't on the ceiling. The other thing I can do is set it into analemma mode, and this is really what the whole point of the exercise was. If I go into analemma mode and again set the time to, let's say, noon, then instead of running on at time, running time on, it's now basically working its way through the noon analemma, and you'll see that the date, we get several days at 28. I don't know if that's legible. Is it legible, Frank?
Well, just, yes, but only just.
Okay, I can make it maybe a bit nearer about that. So you can see that it's working its way on through the year, and it spends 4 times on each day because it works its way through the leap year cycle, thus getting a smaller increment than a given calendar day would. And I can slow this down or speed it up so that you can actually draw it on the ceiling. So if I slow it down this way, I'm changing the analemma interval to be 4 seconds between each move, which would give you enough time to draw on the ceiling. So this was the whole purpose, was to be able to use a laser to draw on the ceiling. So if I now put that away and start sharing my screen, there's a little bit more background to where we are. This is the front room, and here is where the bracket is fixed to the outside. It's quite a big room. It's 5 meters by 5 meters, and you can see that there's a sort of light fitting here which gets in the way. So I had to remove that as part of this project. You know, otherwise I was getting a shadow cast at certain hours and certain solar declinations. This thing was in the way, so I actually removed it. It was sacrificed in towards the, there you go, here we go. So you can see that I've got plenty of clear sky at high elevations because the houses on the other side of the road are quite far away. Looking slightly east of due south, I've got a tree, which in the winter is a nice big horse chestnut. It doesn't cause me much trouble in the winter, but in the summer it gives you a big dead zone where you don't get anything. My house was at 9 degrees declination as read off Google Earth, Google Maps. And this is how I find the easiest way of designing sundials for a given location, is to find them on Google Earth and measure the declination. Here's a picture that's in the article itself. You see the ray of sun hitting the mirror, and there it is on the ceiling. This is my goal. As Frank says, the summer loops of the analemmas are very, very small, and they get very large in the lower solar declinations. Over here is where the laser turret is fixed to the wall we were looking at behind the TV, and the goal is to steer this laser turret to where the sunspot should be. And once you can do that reliably, then you can drive it to where the sun will be at clock noon on every day of the year, or every day in the leap year cycle, and draw a nice analemma or a series of analemmas. You can see that we're not quite east-west in that we've got this declining house slightly by 8 or 9 degrees. Here's my first mistake in this sorry story. I thought it would be good to have a bit of a crosshairs on the reflected image. So I put 4 little mirror tiles set on the bracket. Unfortunately, this wasn't great because they're not all perfectly coplanar, which meant I got 4 random dots in different places on the ceiling. So that's mistake number 1, was rectified by having an actual single piece of glass with a bit of electrician's tape forming the crosshairs. And that gave me quite a nice, well-defined spot for the center of the place where the spot was. And that was good at high elevations, but obviously as elevation decreases, this whole thing becomes less well defined and a large oval. So building the laser, this is my second mistake. So I thought what I need was to put some of these 30p laser diodes, 5 milliwatt red laser diodes, and attach them on a pan tilt hat, which you can buy for the Raspberry Pi. This wasn't great because these servos are the sort of servos you get in radio control models, and they're not designed for high precision and high repeatability. Here you can see I've mounted it on a brick, on a house brick, which I wrapped in brown paper to make it look slightly more aesthetic. But this was fine for pretending to target your grandchildren with a laser, but it was no use for drawing a sundial. My next mistake was to move towards stepper motors. These stepper motors are very cheap, 10 quid stepper motors. Unfortunately, they're pretty precise in precision, but they don't have any feedback on their position. So every time you power them up, they're where they probably were last time you powered them down. So in order to get some kind of baseline, I put some optical, these are infrared optical transmit and receive, and then I would drive the thing around until a little black line here went dark. And again, nothing like enough accuracy for what I needed. I was looking for much better, or around 1/10 of a degree in precision. Didn't manage at all. But then I found these, which are great, and I utterly recommend these devices. They're called Mechaduinos. They're quite high precision stepper motors. These are about 70 quid each now, we're talking. And the way they've solved the feedback from the stepper motor is somebody's invented or designed a PCB that bolts to the back. You put a little magnet transversely glued onto the back of the spindle, the axle of the stepper motor, and you read it with a flux measuring sensor by an Arduino processor on here. So the closed loop of driving the stepper motor position to where you want it to be, which you communicate via USB, is all done locally on here. You have a 3-term controller, PID controller, which drives it very accurately. So these things claim to be 0.1 of a degree, which is pretty much good enough. And I found them to be very repeatable, very reliable. Here we come to my, I think it's 4th or 5th mistake. I 3D printed these cradles, but I'm not very good visualizing these things ahead before I actually make them, in that although I made a nice big gap here for the cables, I didn't make any gap down here for the power supply, which I recovered in the Mark III 3D printing, whereby I've got plenty of holes to get cables in and out. And this is the final configuration. So this is now bolted to a bit of plywood, which is clamped to a bit of plywood, which is mounted on a bracket to the outside wall. So that's nice and stable, fully repeatable. And there it is, and there it is behind the TV, where it lived for 4 or 5 years. A couple of close-ups to show all the wires. Basically, as I said, the Raspberry Pi has got 2 USBs, and it supplies power to the laser. You've seen plenty of that user interface on the TV, and you've seen that picture. So now we come to the problem of, okay, I've got a laser turret that I can steer very accurately and repeatedly in precision. How do I point it in the right direction to where the sun spot should be? And the first step of that is knowing exactly where the sun is in the sky. And all my software is written in Python, and there's a really good library I can recommend here, which is Skyfield. It operates at extreme precision. It agrees with the United States Natural Observatory, and it takes into account pretty much everything you need. So this is how I calculate equations of time. I don't just use, sorry, I say I don't just use, I don't calculate it myself from some trigonometry. I ask Skyfield, what is the sun's azimuth at noon for a given location on Earth on a given date? And that's what drives the equation of time that's used in marking out these analemmas on my ceiling. So the first step in trying to decide where to point is to define the axes, define your coordinate system. So I put the origin directly above the mirror on the ceiling. I'm assuming that the ceiling is a plane, a horizontal plane. And that is a big mistake. I think that's the root cause of why the whole thing was much less accurate than I'd hoped originally. So X is in the east-west direction, and the laser turret is here behind the TV. So you could try and measure all these. So to get a mathematical model, we can pretty easily figure out, we know where the sun is from Skyfield. From the mirror is down here, so the spot will be up here. You can kind of work that out by pretty easy vector maths, assuming you know what the Z dimension here is accurately, and where the where that's all you really need, and that will define your XY position on the ceiling in these coordinates. But unfortunately, there's a lot of other things you have to take into account, and this is where somewhat came unstuck. Because if we're trying to get an accuracy of position on the ceiling of less than a centimetre, across the whole ceiling, you need accuracy of better than 0.1 of it, or bound 0.16 of a degree. And that means if you just stuck your mirror on a bracket, it could easily be up to a degree off horizontal in either of those two axes. And if you're a degree out here, then the sunspot will be in a very repeatable position, but it won't be where you calculate it to be. So you need to kind of estimate this. You can't really measure it to good enough accuracy. You have to estimate it. And then we've got a load more things that we need to take into account when we're running the mathematical model to decide what pan tilt we should have. Here, this is a top-down view. This is the center of the pan servo's axle, and this is the tilt servo's axle. The laser is stuck on the end of the spindle, which isn't directly above it. So you need to take that 2 or 3 centimeters into account. Again, you can't measure it accurately enough, so you need to estimate it. The laser might not be stuck on precisely orthogonal to the spindle, so it could be a degree of error there, which would give you more than a minute of error on the ceiling. Similarly, there's a whole more. I won't go through each of these because it's a bit tedious, but basically the base I've mounted the thing on may not be perfectly horizontal in each of 2 dimensions. And this cradle that's holding this, the tilt servo, might not be perfectly horizontal either. It might be sagging by a certain number of degrees. So I've got to estimate all these. How do I do that? Okay, well, how I do that is by marking on the ceiling actual dots of where the sun was at any given time and date. So when I had a full sunny day and nothing else to do with my day, I would be jumping up on a chair every 10 minutes, or in this time-lapse video, every hour, and then putting a little dot at the center of the sun's image on the ceiling as the clock struck, or as my little program on my phone told me it was the right time to do it. So you can see you end up with a series of dots in a quite plausible line. And now what I'm going to do is use the known time and date of that dot and the pan and tilt the pan and tilt of the, I'm going to manually steer the laser to beyond that dot and then note down what the pan and tilt is of that dot. And therefore I can add those two things together. And if I have enough dots, I can say, right, I know what pan tilt I need for every one of these dots. I know where the dots should be because I know the time, the date, and the, so therefore I know the notional X, Y on the ceiling. Therefore, that will allow me to calibrate out all these little parameters in the model. That's the theory. And that is the theory that nearly broke me. So if we look, here's another picture of a nice, that's a good day. So there's a yellow dot for an hour, and then there's a 10-minute dots, and then there's another dot, yellow dot there for another hour, etc. So you can see this is the end of a long day with me jumping up and down, marking these dots on the ceiling. And here's some dots. So these are hours. You can see they don't exactly line up because my precision in sticking these little sticky dots on the ceiling is not necessarily as good as it should be. Equally, you can see it, this is a kind of February time scale. You can see the sun spot is now quite elongated, and it gets pretty difficult to estimate where is the center of that spot. So you can easily get a centimeters error in placement of these dots. So by the end of several years playing this game, basically I said it's 7 here, but actually there's 9 good dates that it says in the article. There are 9 dates on which I had a decent number of dots, and they vary from the summer solstice, near the summer solstice in 2018 and 2019, through to basically as the dot, this way is north, so this is a dot left the ceiling or came onto the ceiling, which is February. As you saw from the original picture, at the actual winter solstice, the far end of the dot is on the wall, and it's left the ceiling due to the length. So I end up with 107 dots, 107 reference points. So for instance, this is the 27th of June, 0900. The pan is 99.96 degrees and the tilt is 49.64 degrees. So I've got 107 reference points that I can use to calibrate these damned 13 parameters that I need. So here is an estimation run. I use a hill climbing method, and I won't go into the detail because it's pretty tedious to people who like nice brass sundials, but you can see these are 13 parameters, and I'm adjusting, nudging each parameter to see if the overall error between the actual pan tilt and the predicted pan tilt using the current model. If you imagine there's a pan and a tilt that the model tells me to point the laser in, but I know what it should be for that time and date. So I can calculate an error in pan tilt, which must be due to my parameters not being right. So what I do is adjust each parameter in turn, and if it improves that error, so I recalculate all the errors on all the reference points. If it improves it, I keep it, and then I move on to the next parameter. So I'm nudging each parameter in turn and working my way up the hill. And if the whole function of this model was linear, that would be a nice single hill, and you would climb the hill and you get to the optimum spot and you'd have no errors. Unfortunately, because it's a very non-linear function, there are plenty of local maxima. So the hill climbing tends to get stuck in a local maximum very easily. So each of these runs takes, it iterates there through about 13 parameters times about 30 or 40 iterations before it's converged. and I can run as many of these as I like. So you can see, as I was about to leave the house, by August 2023, we'd sold the house. We were just waiting for completion. So this whole project was now on life support, because I knew I was going to be leaving the house within a month. So I had a kind of last roll of the dice to try and find an optimum and draw these analemmas. So I ran 2,600 runs. It took 3 days, running 24/7. And for each of these runs through the day, you can see I was getting down to about 0.02 of a meter. So getting to around 2 centimeters accuracy on the trained points. I also mapped that into seconds of time telling error. And you can see I'm operating around the 60, 70 RMS root mean square time telling error, which is again far worse than I was hoping for. I was hoping for better than a minute and better than a centimeter, which I didn't manage to achieve. These are the final parameters I ended up with in the best run of all, which was on the 10th of April 2023. If we look at these 2,700 runs I did, you can see the parameters are all over the place. This is due to the Monte Carlo approach of trying to do this hill climbing, getting stuck in the local maxima. You can see that there's a series of errors down here around, again, the best I get is around the bit less than 2 centimeters. I won't spend any time on this picture because it probably melts people's brains, but essentially all these green dots are reference points on the ceiling. The red lines show the error on this particular calibration run. This error is magnified by a factor of 10, so you can see them. Otherwise, it'll all just be little red blurs. You can see that there's there's not a systematic error profile. Some dots clearly are in the wrong place, in that the error of its neighbours are sort of northwest, but the error on this one is slightly east of north. So clearly this dot is in the wrong place slightly, and so on. But I'd run out of time to do any more playing, so I decided to cut my losses. There's a little video, there's another time-lapse video of, here's the sun spot, and there is the laser trying to track it. And this was an early run in February, so I did better by the end. But you can see that it's kind of more or less tracking it. If I then move on here, there's another example. So finally, I decided to just take one of these runs and draw these down analemmas on the ceiling. So you can see here it is running in the analemma mode, and it's pausing 12 seconds between each move, so I have a chance to mark it on the ceiling. And it took me about an hour to do each of these analemmas. So here is the noon analemma finished. And if I tidy up the contrast on those pictures, you can see that it doesn't run straight through all these dots, but it's not many centimeters off. It's like 1 or 2 centimeters off. And it also misses these dots. So this is the noon. This end is summer solstice. This end is winter time. So this is the spring coming in, and here's the autumn going out. So having drawn that analemma, I can then draw the other analemmas. Finish the whole, sell the house. And I can't take it with me, it's on the ceiling. And this is all the analemmas drawn. So I'm now standing at kind of the south end of the room, looking up at the ceiling. You can see I've removed the light fitting that was irritatingly in the way. And that's basically what you get. That's a more kind of horizontal view. And here it is with the markings up. I didn't actually end up making it aesthetically pleasing. We hadn't got as far as discussing what it would actually look like, but these are the construction lines, I think I would probably paint in pastels the insides of the analemmas. As we all know, if you're drawing analemmas, you can't really have them every half hour or every quarter hour because they start to overlap. So to avoid it just being a confusing mess of scribble on the ceiling, I decided to have it just an hour each. And here's a typical case where there's no sunshine, okay? It's 2 p.m. BST, 1300 GMT, and the laser, funnily enough, is right on the analemma because the analemma was drawn from the laser point. Who knows where the sun would be? It kind of doesn't matter because it doesn't sun very much. So what you have here is a very hard to read clock. Basically, how to think of it. And that is the end of the story. So I had to leave it behind. It doesn't work very well. If I'd had another 2 years, I'd have probably improved a number of things about it. The main issue is that the model assumes that the ceiling is a horizontal plane, a flat horizontal plane. And this is a 1920s Edwardian semi, and I don't think that ceiling is a horizontal plane. So there's an assumption built right into the very beginning of the model that's invalid. And I can't try it all again in my new house because I don't have a south-facing room. There we are. Any questions?
Well, thank you very much. Martins, can you see any raised hands?
Currently, no raised hands, but you are welcome to ask questions.
It's certainly an amazing effort, Andrew, for I would say middlingly good results. Yes, it's on the way.
Jeffrey, please.
Good afternoon. I'm wondering, did you consider putting the laser turret co-located with the mirror to take away so many of these variables?
Well, you can't do that without it casting a shadow on the sunspot. So actually making it co-located, it would be a few centimeters away anyway. So you'd have to accommodate that XYZ offset, in which case you might as well accommodate a larger XYZ offset. I think I did originally have in my head to have 2 lasers, one each side of the room, and also they're not very attractive things, and I do have a family using it as their front room. So although the mirror was fairly discreet, the laser had to be hidden behind the TV. But it's interesting. And I discarded the idea of having 2 lasers because then any errors would have been extremely obvious. It's like, you know, with a clock, you know what time it is. If you have 2 clocks, you don't know what the time is anymore.
Thank you.
Possibly I have a question. I think I've seen a reflection sundial in Horniman's garden library. And if, for example, some other library would be interested to lay out all those analemmas, how much time actually would it take for you to set up those lasers and then to calculate all the analemmas and positions of those dots?
Well, I think if their ceiling was a plane, so I could just use the software as it stands at the moment, all you need to do is collect some reference dots. So it's quite important to have that your dots have a good diversity, as much diversity as possible in the angle of the lasers. One of the issues here is you can imagine that there are confounding variables. If you imagine that the mirror is tilted slightly up in east and the laser platform is tilted slightly up to the east, you can't really distinguish which of those is the case. You know, they basically move together until the dots are a long way away from the east-west plane. So you need some dots close to the summer solstice, you need dots down at the winter end of life, and you need early morning dots, and you need midday dots, and you need afternoon dots. But so the time consuming part is really you need a good 7 days worth of sunny days to get a load of dots. After that, running the the software would just work because it would estimate X, Y, and Z of the laser, pan tilt errors of the laser, mounting errors of the laser, mounting errors of the mirror, quite happily. It has no preconceptions as to what the geometry is. So it wouldn't take very long. Yeah, it wouldn't take very long. And then drawing, following the moving laser dot during drawing the amalema takes about an hour per. So you could do it all if you visited every few months on a sunny day. It would be about 6 or 7 days work, I think.
But the initial dots should be laid out during summer solstice or any date?
Any date,
works.
as long as you know what the date is. So it's good to have some summer dots and some winter dots and some equinox dots. So you've got some diversity in the angles of the laser.
But basically, it's not a question of days to lay it out, but we have to wait for weeks and months to test those points. It means.
Exactly. So you need to visit the site across a year. Occasionally across a year is basically it. So if you went 7 days throughout a year, you could collect the dots. If there were 7 sunny days in a year, you could get enough dots to be able to play this game.
I'm just wondering if somebody wants to commission Sundial like that, it would be hard to convince on such a long time.
Well, this is done for love. So this is done for my own entertainment after I retired, basically.
Andrew, a question from me. Could you consider doing the traditional way, instead of having a mirror, having a pool of mercury, because that at least would be level?
If it rained, unfortunately, the pool of mercury would get spilled onto the floor and kill the bougainvillea.
I'm not sure it would. Mercury is much heavier than water.
Right.
And you can squirt water on top of the surface of.
I think the toxic fumes would also be looked down on by
these days, health and safety would be a problem. Yes, that's true. But in my young day, we splashed mercury about all over the place without worrying unduly.
I have a little 5-minute bonus if you want to see that. The sun tracking shade. Are you interested in that? Have we got time?
Is that the one which you showed me earlier?
Yes.
Yes, let's just do so that. Anybody who's finished, just do feel free to leave. But these 2 videos are quite fun.
So as a kind of spin-off, it's a spin-off project of that whole game. Is in this south-facing room. I've got 3 seats on the sofa and 2 over here, and I usually sit here in seat alpha. And the problem is when the sun is low elevation, it can be very irritating in your eyes, and you can be jumping up and down and moving the curtains or some roller blinds. So I thought what you need to do is have a Raspberry Pi driven shade that moves across the window. So it's a very similar set of maths, but it's a lot simpler in that you're calculating where the sun's ray intercepts the plane of the window, or rather plane in which the shade is hanging, and then uses 2 bits of string. So here's the 1/2 meter diameter. It's basically tissue paper on a cardboard ring, and there's a little bit of a coat hanger wire stretching across here, forming a cord, and then there's 2 bits of fishing line going on from this side, one from that side, which basically allows you to do some maths. So I've got 2 drums here, which are driven by the servos that were discarded from mistake number 3. So mistake number 3, I had 2 little stepper motors left over. So I used them, 3D printed a couple of drums, and the only bit of tricky maths was if A and B aren't equal, then this cord isn't horizontal. So you need to iteratively calculate where the cord will hang, where this backstay will hang for any given position. So here's a little drums, and these are the old servos that you saw earlier, stepper motors that you saw there. And here's another Raspberry Pi. So I do like Raspberry Pis. So if we, there's a little video of them reeling in the little fishing cord. And then I've got a tiny little quick video of, just need to move that out of the way. Here we are. So here is currently tracking to shade alpha, which is that clock pillow. Away. And the next adjustment is in 5, 4, 3, 2, 1. Here it goes. So here's this picture.
Okay, Google, sunshade Bravo.
And it's all wired into my Google Home. So I used a if this then that webhook to talk from Google Home into the Raspberry Pi, which has an exposed API over the internet.
Sun shading Bravo, which is this middle seat on the sofa.
Here's where I sit.
Alpha is now exposed.
So if I
Hey Google, sunshade Alpha.
I'll cancel that and move on to the last video, which is this is much more of a success, I would say. I just want to get rid of that, and then I can do that, and then we get full screen. There we are. So this is seat echo, and you can see the sun is moving, and the shade is perfectly shading somebody's head sitting in that seat. And then you can see as the sun moves around, seat echo is no longer in trouble. And this is seat alpha where I tend to sit. You can see it's perfectly shading my head as I sit there reading the newspaper or trying to figure out why my parameter estimation hill climbing isn't working very well. This is much more of a success. And people wonder, what is this yellow circle that traverses across my front window? There we are. That's it. That's me. Done.
Well, thank you very much. And thank you everybody for coming. And well, it'll be one approximately July the 23rd for the end of the June issue of the bulletin. So I think that's all from us. Anything for you to say, Martins? You might point out that on the website, on the YouTube channel, you can see all the videos associated with World Sundial Day. Perhaps you can draw attention to that.
Oh, yes, on March 20, we had a very nice event. It was World Sundial Day online conference, and there are all presentations recorded. These are short videos of some 20 minutes long, and you can watch them and see different presentations from that conference.
Yes, well, and thank you very much for hosting this evening's meeting.
Yep.